Sometimes it is hard to prove or disprove the convergence of a random sequence. So we have some necessary and sufficient conditions that if they are satisfied, a random sequence is necessarily converging or is sufficient to converge and so on. So these theorems are very handy, and then I will go over them. I will not necessarily prove them, but you should be able to use them. So necessary and sufficient condition for mean square convergence is something that is mostly handy. So the theorem is that a sequence of random variables, x of n, if it has finite power, if it is second order moment or expected value of its absolute value, converges. So a random sequence converges to a random variable with a finite power. So if the powers are not finite, this theorem is not valid. If and only if you have a Cauchy convergence. So it means that if this is like time, and then if you go beyond certain point n, and then if you choose arbitrary n and m, if both have n and m are bigger than n, then you could reduce the distance. You could reduce this one to an arbitrary value, or in other ways you say that limit of these converges to 0. So if this condition is satisfied, then there exists x such that x of n converges to x in mean square or in L2. Okay, and the other way around. So in other words, if you have L2 convergence, you have a Cauchy convergence, and if you have the Cauchy convergence, you have the L2 convergence. So it's necessary and sufficient. In this side of the theorem, you don't have the converging point, but in this side, in the side of definition, you have x. So it means that if you have Cauchy convergence, even though you may not be able to find x, but you know that it is guaranteed that it will converge. And this is what we need in machine learning, in adaptive algorithms, and so on. So you will see that the errors or the difference between the values of x of n and x of m reduces to any arbitrary value, and in that case you say that x of n is converged in mean square sense. So the proof, the implication from this one, because you can write this one, you could say that if x exists, you could add x here and then minus x. So you could have minus this one, and then consider this one with this one, and this one with this one, and expand it and say that you have this inequality. So always this guy for any random variable x, okay, you have this one. Now you could say that limit of this side is 0. So therefore, or if the limit of this side is 0, if you have the convergence, if you have x of n converges to x in L2, when you take limit, because we know that this is bigger than 0, then the limit of this one shall be 0, limit of this one shall be 0, therefore this should be 0, and therefore you have this one. So one side of the theorem is very easy to prove using this inequality. The other side is also very easy. So what we could do is that assume that this is true, then we take a subset, because this is true for any m and n. So I could choose nk as a subset of integer numbers, such that because I could make this number as small as possible. So I choose the first nk and the second nk, nk plus 1, so this is nk, such that the distance between these two is 1 over 2 to the power of k. And then I increase k such that these are... and then what I do, I add these guys together. So I put a summation over k over this one. So so we know that this sum of these, so for such a sequence, I define sk equal to this one, and I prove that this is exercise for you, that these will converge to random variable x. Okay, I think you don't need this absolute value. So so to prove that these will converge, so you take this sum and then you use some equality similar to this one and apply it. So I leave the rest and details to you as exercise. It's not very hard, and that's it.